Start.
Okay. Good day, good day, good day, and welcome to Africa Teen Geek. Okay, this is our STEM online school, and if you have just joined us, this is the grade 12 physical sciences class. This is a grade 12 physical sciences class. I hope that you're in the correct room and you are ready to do some learning today. Okay, today is a Monday, and we have started last week with the work, energy, and power. Yes, we started with the work, energy, and power. So I hope that everybody has been following through because we first started doing work and we completed work. We did all the problems that have to do with work. We did energy, the work energy theorem. We did conservative forces. We did non-conservative forces and the formulas that go with them. So that I hope that all of you are still keeping that in mind in order for you guys to be able to understand because everything follows through all the formulas you did when you calculated the work done. You needed them for the the work energy theorem and the conservative forces and non-conservative forces, and up until now that we're doing the power, we're still going to need all those formulas and all that background that you did from the beginning of this chapter. Okay, so my name is Nonkululeko Matondo. I am your teacher for Physical Sciences Grade 12, and I hope that you guys are ready for a beautiful lesson. And as per usual, you have done your homework because we're going to start with the homework and do some corrections just to make sure, tap into your brain cells and see um, if you guys are grasping the procedure. That's why I always give you guys homework so that you guys can go home and practice some of the work that we get to do here. Okay. Um, what I also wanted you guys to know is that here we work from the Sia Vula textbook and the Study and Master textbook. So if you do have one of those or any other one, as long as it's CAPS approved, it's a textbook that we are using right here. But if you still need some more textbook, you can go download yourself some Snaplified. Snaplified is an app that it's an app that you can download all your textbooks, and they've made all textbooks free this year up until the 31st of December because of the whole COVID-19 issues. So they've made this great deal for us. So please, if you do get a chance, go in there, get yourself some Snaplified for all your other subjects as well. It's not just for physical sciences, but it's for all your other subjects as well. Okay? So moving on, let's get to know more about power. But before we go there, let's do our homework. Okay. Looking at our homework. Okay. Sorry about that. We had this homework for today. Okay. It says a 60-kilogram skier with an initial speed of 12 meters per second coasts up a 2.5-meter high rise as shown in the figure. So here's your skier and he's trying to move up this slope, okay? So find her final speed at the top, given that the coefficient of friction between the skis and the snow is 0.08. So traveled, find the distance traveled up the incline, assuming a straight line path as shown in the figure. Okay, so there we have it. Already this is a triangle for us. So we already have the angle and we have the height. Okay, so we've got the angle and we've got the height. So how do we find her speed at the top? They're looking for V1 here. So which means that kinetic energy is also going to be calculated right here. Okay, so here let's see if we have coefficient of friction. So we also have friction. So which means that in this equation, we do have we have the work non-conservative. Because remember, work non-conservative is the friction in this case. Okay. So we need to determine the length of the slope as this is the distance over which friction acts, okay, as well as the normal force of the skier on the slope to determine the magnitude of the force due to friction, okay? So the normal force balances the component of gravity perpendicular to the slope thereof, okay? So friction, obviously, it's one that's opposing the motion of the force, the normal force, basically. No, not the normal, the applied force, okay? So friction is going to be minus the coefficient times the gravitational potential energy, okay? So it's going to be minus this, they've given us the 0.08 times the force, gravity, and times the cos of theta, okay? So it says here the length of the slope will be triangle H, which in this case is H over sine theta, okay? Remember, what we're doing here, it's opposite over hypotenuse. No, yeah, it is opposite over adjacent, okay, in this case. So it's going to be H divided by sine theta. In order for us to find this distance, we need to find this distance here at the bottom, okay? We need to find this distance here at the bottom. So we know sine theta is equals to H over triangle X, and this will give us what we have here, okay? Our sine theta will be 35 and our H is 2.5. So now we go to our equation, okay? We know that work non-conservative is equals to potential energy, change in potential energy plus change in kinetic energy, right? So what has been done here is that we've grouped them like we did, remember with the problems that we did last week. We grouped them together. The initial ones, we put them on one side, and the the final ones, we put them on one side. So this is the kinetic energy final plus potential energy final, okay? So now you're going to break them down, all of them accordingly, because this one, it's this basically, but now it's broken down because remember now our triangle H is equals to H over sine theta. So we also have to have that as well, okay? Because remember what our work done is. The reason why they have the friction and the change in X is because work done is equals to force times the distance. So that's why we have the H over sine here. And then we have our kinetic initial, potential initial, and this will be equals to the final one, which is this one that we find right here, okay? So this is how we've broken everything down. And now we're going to slowly, because we're looking for the final velocity. So we're going to keep moving everything to the other side, until we have VF as 1, okay? So this is what you get, okay? And then you start putting all the values that you have in there. And this is what you're going to have. And you square root the VF because here it's squared. And your answer will be 9.46. Okay? I hope that everybody is together with me. And if you are a bit confused, just drop me a chat and I'll try to explain some stuff to you, wherever it is that you're getting lost, okay? But basically, this is what we have for this problem. And this is the homework that I gave you guys. for us to practice the um, work, energy, and this was the non-conservative calculations. Okay. So today, what are we doing today? Today, it's not much that we're going to be doing. We're just going to be doing power. Okay. Power is one of the stuff that we have to do actually remember it's work, energy, and power. So now we're doing the third element, which is the power element, okay, of this chapter. So we're going to be finding out what is power, how is power derived, um, how it is calculated. We're going to have calculating power and how it works with the the work energy theorem, the non-conservative forces and conservative forces calculations. Those are all the things that you're going to need because they also all relate to power. Okay, so we also need to do the minimum and maximum power. Okay, also going to find out what that is all about as well. Okay, so let's get started. Okay, power. What is power? It says here that power is the rate at which work is done. Okay, so you have work, but now it's according to time. So that thing makes it a power. Okay, so power is the rate at which work is done. Okay, you can also say that it is the rate at which energy is transferred to and from a system. Okay, so this is the time they're going to want to know from 0 seconds to 20 seconds, this and this and this happened. Then now you can find your time because you've got a rate that is indicated. Okay, so power is easily derived from the definition and expression of work done, basically, because this is a work done. And work done, it comes in different ways. It could be work non-conservative, work conservative, network, or, friction work. Like it could be anything. So this is an expression. The power is derived by this expression, but now it races against time. Okay. So the rate in this case is actually the change in time that work is being done. Okay. So it's not just time where you're gonna say just 5 seconds. It's from changing times from point zero to point F, point I to point F. So that's the time that you're going to most likely be working with. Okay. So it says P is equals to work divided by time, and work is this. Remember what I told you. Work, it can come in different forms. So time, you're just going to be dividing it by the time, but the work part is everything else that you've done in this chapter, all these calculations that you've done in this chapter. Okay. So in the case where the F and the triangle are in the same direction, we know it will be positive. If we do an equation of this nature, we'll say F is triangle T, and then we put them together. And if we remove this F, triangle T divided by time will give you the velocity. Okay? And so the P is power, the F is force, and the V is velocity. Okay? And the triangle X is the distance or displacement. Okay? I hope that we are together. And if you don't understand something, just go back and I'll try and explain it to you. Okay? Then moving on. Okay, I'm just trying to get to the next slide. So basically, you understand what's happening with power. Power is the rate at which work is done. So those are the most important things that you have to know. So now we've got a problem, okay? The power calculations. It says a girl pushes a 5 kilogram box for 5 seconds along a 10-meter horizontal surface. Okay, so you've got your kilogram, and you've got your time, and you've got your distance. Okay, she applies a constant force of 20 Newton on the box. Calculate the work done by the girl on the box and calculate the power of the girl. So this is the simplest question that you can get in this regard. Okay, so number one, it says work force is going to be the F triangle X cos theta. But because this one, there is no force that is acting against it. So it's going to be cos 0. Okay? As you can see there, it's cos 0 because there's no friction. Um, the force and the distance is moving in the same direction. And this is going to give us 200 joules. Okay? So the work done by the girl is 200 joules. So now, for us to find the power, now we need to divide the work divided by time. And this will give us 40 watts. So the power of the girl is 40 watt. Okay? Are we together? So I just want to check some more examples that we can look at on the Siyavula textbook. Okay, so the computer is a bit slow today. I don't know why. But I'm just trying to share the Siyavula textbook so that we can do some more problems. So guys, we're almost reaching the end of the chapter for this work, energy, and power. And it was quite a nice you know, chapter. I hope that you guys, as much as me, also enjoyed going through this chapter. I don't know, it just doesn't want to doesn't want to share my screen, so I'm just trying to share the screen. Okay. Okay, am I still live? Can you hear me, TJ? Yeah, this is a way for us to calculate power. I think I was about to go to the examples that we can do on a textbook. It's always important that we refer to a textbook because a textbook, they usually have many problems, dealing with these kind of things. So I'm just waiting for it to share. Okay, so guys, I'm so sorry about all the, problem that we've had. Okay, my Zoom has not been doing so good today, but I wanted us to do a couple of, the problems that you've been dealing with that have to do with power. Ooh, okay, so for now, let's just move on because it seems like I'm having a problem opening up my files on the system. So I think we'll just go back and do our slides and okay. So let's just move on for now and we can work with what we have here because I still have some stuff that I wanted us to talk about. For example, the power calculations. It says here machines are designed and built to do work on objects. All machines have a power rating. Okay. The power rating indicates the rate at which machine can do work upon other objects. So basically, an example of that is a car engine. Why? Because it has a given power rating. Okay, the power rating relates to how much rapidly the car can accelerate. So you can see usually you also have that indicator that shows kilometers per hour, and the faster you go, the more you're driving at kilometers per hour. So that all has to do with the rate. Okay, that you can drive 60 kilometers in 1 hour. So depending on how fast you are driving. Okay, so a car with 4 times the power rating, for example 200 kilowatts, could do the same amount of work in a quarter of the time, for example 0 to 60 kilogram in 40 seconds. Okay, so the power, um, and you can see, I have a picture here of something like if you put too much power, I don't know what the guys call it, exhaust or something like that. But the more power your car has, the faster it can go, okay, in a less amount of time. Because why? Power is all about rate, okay? The rate of change of the work done, which in this case, the movement of the car gets done in a short space of time, okay? So, power calculations. It says here a car travels along a flat road at a constant velocity of 12 meters per second. If a constant friction of 20 Newton acts on the car, determine the power developed by the engine of the car. Okay, so it says here since the car travels at a constant velocity, the magnitude of the frictional force must be equal to that force exerted by the engine. Okay, so that means if um uh the force is 20 Newton, and the power developed will be P is equals to F times V. So we don't need to break it down because they've already given us a velocity. So this is a very, very short version of our power calculation, okay? So it will be 20 Newton times 12, and that will give us 240 watts. So the power developed by the engine of the car will be 240 watts, okay? So moving on, we're still on the power calculations, okay? It says an electric pump is used to raise water from a borehole of a depth of 20 meters. If 600 kilograms of water is required every minute and the water needs to be discharged at 6 meters per second, what should the minimum power of the pump motor be? Okay, so now we know we've got a depth, we've got the S, we've got the kilogram, and we've got the velocity. Okay, so assuming there's no friction between the water and the pipes of the pump, the only non-conservative force acting on the water are the forces exerted by the pump to raise the discharge and discharge the water. So the energy required to raise the water from the borehole and to discharge it is the same as the work done by the non-conservative forces. Okay, yes, because remember they have to pump it up, they have to push it out. So now the work non-conservative is going to be triangle K plus change in potential energy. Okay, so for this one it's going to be 0 for both initial. Okay, so it's final minus initial plus final minus initial. Okay, so it's going to be half 600. You're going to plot everything that you have, and this is the answer that you're going to get. Okay, so therefore the minimum power required to raise water and discharge it will be this that you've just calculated divided by the time, which is 1 hour, and that will be 2140 watts. Okay, I hope that that makes sense to you. But remember, I told you that as much as the equation is W over triangle T, the W, which is the work done, will always be your biggest challenge to overcome, because work done has so many laws, has so many different formulas that you need to work with. So this is a work non-conservative force. So this is how you need to, this is the equation that you need to use. But sometimes you could have had something else. Okay, so they say water is a scarce resource in South Africa. In many parts of the country, the surface does not supply sufficient fresh water to meet the demand. So while the luxury piped water is often taken for granted in most urban areas, in many rural areas, people still rely on wells and boreholes to extract groundwater. Okay, but it's not just in rural areas these days. Even people that have their own plots and own, yards, they're moving over to boreholes because number one, water has become so expensive. Number two, um, it's just tough. Sometimes there's no water, and the scarcity of water is also the reason why. Okay, so boreholes are similar to wells, although wells are usually shallower. They tap water from the upper soil, subsoil water. This means that wells do not usually penetrate an impervious layer of the soil. Deep wells and boreholes usually draw water from below at least one impervious layer. In both cases, however, water needs to be brought to the surface. In a traditional well, water is raised using a pail or a bucket, so it's quite easy to get water from those traditional ways. Okay, so boreholes use a mechanical device to drill into the ground, and if water is present, it has to be pumped to the surface. So that's a bit of a engineering perspective. So pumps can either be mechanical or electrical, because mechanical or electrical energy is converted to gravitational potential energy. Okay, so in many rural areas of South Africa, people have to physically pump the water to the surface. I don't know if you've seen the videos where there's those little pumps that look like they are so strenuous that they use to pump water. So this requires a significant quantity of energy, and this energy needs to be transferred at a reasonable rate. Okay, so if, for example, the pump raises water from the depth of 20 meters at a rate of 2 kilograms per second, this means that 2 kilograms of water must be pumped to a height of 20 meter every second. So the minimum energy required would be the work, which is the gravitational work that we're going to calculate. So it's going to be mgh, because it's gravitational potential energy, right? Like they mentioned there, that will be the gravitational potential energy. And then the minimum power after we get our work will be work divided by change in time. And in this case, it's 1 second. And this will be our answer. So this power output is equivalent to 50 kilogram person walking or running up a flight of stairs 10 meters high in 12.5 seconds. So you see, power is a very interesting thing as it works according to time. So maximum and minimum power. Here I just wanna, go through a bit of it. It says the maximum power output of an electric pump is 30,000 watts. It is used to collect water from a borehole 25 meters below the ground. Okay, so if 100 kilogram of water is required every second, calculate the speed at which the water is discharged if the pump operates at a maximum power output. Okay, so here it says consider 100 kilogram of water being raised and discharged every second. If the pump operates at maximum power output, then the work done by the pipe or the work done by the non-conservative force would be in this case. So we're going to use the work non-conservative. Okay, so I think we're slowly establishing that when we're dealing with pipes, it's work non-conservative. Okay, so it's going to be, we're already plotting your 30 watt because it's been given, and the time, which is 1 second. So the work non-conservative becomes this. So you go back to your equation of work non-conservative, and you know you only have mgh plus half mv squared. There's no change. Okay, this is a pump action. So mgh is going to be 100 times 9.825 plus the half 100 kilogram times v squared. What are we looking for here? We are looking for the velocity. Okay, and then we calculate the velocity, and therefore water is discharged at 10.49 meters per second. Okay, are we good? So you sort of understand, number one, that pumps always work at a non-conservative energy, and the initial KE and KP, KE and PE will be 0. So you only calculate the final ones, like the EK final and the EP final. So these are a little small things that you guys need to know when it comes to these kinds of calculations. Okay, so this is our homework for today. The homework is as it stands. It says 2 students, Bill and Bob, are in the weightlifting room of their local gym. Bill lifts 50 kilogram barbell over his head 10 times in 1 minute, while Bob lifts the 50 kg barbells over his head 10 times in seconds. Who does the work the most? Who delivers the power the most? Explain your answer. So what I want us to do, you can do 2, 4, and 6, and those are the homeworks that we'll be doing for tomorrow. Okay, so thank you guys so much for a beautiful class. I am Nonkululeko Madondo. This was your physical sciences grade 12 class. You guys can send me any queries to t33teendlovu@gmail.com, and I'll be able to attend to all your problems. And please keep well. Let's continue working hard and doing some more physical sciences for grade 12. Thank you and goodbye.